All right. Thank you, Trygve. Thank you, Sture, for the invitation. You can tell this is a very important meeting when Martin Head Gordon wears a jacket. And thank you, Andreas, for encouraging me to talk about, the elephant in the room. I'm not the elephant. All right, so let me just get to it. So what do I mean? So entanglement here means the appearance of substantial multi-determinant character in the wave function. So this is also called static or strong correlation. But in regards to what Axel said yesterday, what I have in mind is something more general than left, right, or spatially localized non-dynamical correlation, which is what happens typically in bond dissociations. So that is a type of strong correlation, but what I have in mind is a more general picture, and I'll give you details in a little bit. So how does Consham deal with the appearance of multi-reference, multi-determinant character? Well, it does the same thing as Hartree-Fock. It breaks spin and outer symmetries. It may do it a little bit later than Hartree-Fock, but that's what it does. Traditional functionals, we are taught by my friend and colleague John Perdue, should be on the spin density. So we do unrestricted Consham. And the question is, can we get away with symmetry break-in for describing all types of strong correlation? So let's take an example, the prototypical example of H2 dissociation on the restricted surface. So we have sigma G and sigma U molecular orbitals. They become degenerate as R increases. The ground state gets entangled, okay? And RHF perceives the appearance of a competing determinant, and in reaction, it breaks spin symmetry. Symmetry break-in reopens the orbital gap and lowers the energy. But a very important point, which I'm not sure is always emphasized, is that this mechanism of symmetry break-in, it only lowers the energy. It does not remove the entanglement in the wave function. As a matter of fact, it makes it worse. You see that the UHF overlap of the Slater determinant with full CI is actually smaller. The energy has dropped, but the entanglement has gone up. The full CI, of course, then has a first dominant coefficient now that is smaller than in RHF. So we can argue that this is a case, in this particular case, strong correlation appears from so-called spin fluctuation. This is spin symmetry break-in, spin instability. And unrestricted Consham captures the energetic effect, which is what John was talking about, this frozen frame interpretation. In reality, the wave function is getting entangled. You can think of it as an open shell singlet, but you only keep one of the two configurations, not both. So, some caveats. Number one, let me ask this question. If a system, your system, does not break a certain symmetry spontaneously, like spin here, is breaking it on purpose useful? Well, the answer is no, because any broken symmetry reference will have higher energy. Otherwise, the symmetry will break spontaneously. So there's an important symmetry in electronic structure theory, which is number symmetry. And as Elliott-Liev showed us a long time ago, it will not break spontaneously in mean field for repulsive electronic systems. It will break for attractive systems, but the electron-electron interaction is repulsive. This means that the mechanism at play observed in the spin channel that I just told you about is not accessible in this other channel, which is called the pairing channel. Number is a symmetry associated with pairing fluctuations. It's an SU2 algebra. We call that the pairing algebra as opposed to the spin algebra. Now, when you look at this from a many-body couple cluster sort of perspective, the spin channel is a ring-type channel, all right? But the pairing channel is related to the latter terms. So if you do couple cluster, we're talking about different types of terms in the many-body expansion. So how would you take care of pairing terms, pairing, strong pairing correlations, if number symmetry will break? Well, you will use a BCS or Hartree-Fock-Boggle-Lyubov reference data. Now, these type of correlations are observed in the two-dimensional Howard model away from half-filling. This is a model we have studied with the Simon's collaboration, many different type of many-body techniques. We did a couple cluster calculations, and to my surprise, we were doing unrestricted CCS-CTQ, and we will not even getting close to the right energy that people with other methods, I can talk about it, were getting. And why is that? Well, because break-in symmetry, spin symmetry, is not sufficient to capture this renormalization of the ladder terms that occur when in the Howard model away from half-filling. We also observe this in the low-density uniform electron gas when it gets strongly correlated. If you do regular couple cluster, it blows up. But you can obtain very high-quality results if you screen couple cluster, and you do it in a very specific way, which is to keep short-range ladders with a side radius type of screening and long-range rings. That works very, very well. We published that, I don't know, 15 years ago in PRL. Now, are these pairing correlations relevant for chemistry? I think so, I believe so. But probably not in the upper part of a periodic table. That's why yesterday I asked Axel, how many transition metals do you have in that huge benchmark set? But they're very relevant for high TC superconductivity, for correctly predicting band gaps of monoinsulators. One of my favorite functionals is HSC, which does very nice band gaps of semiconductors. And it's very, very widely used in material science. But the band gap is obtained for the wrong reason. It's obtained through symmetry breaking. Monoinsulators are antiferromagnets, but they are short-range entangled. They are not broken symmetry, spin symmetry materials. Caveat number 2, and I'm not going to go into a lot of details, I don't have enough time. Not all strong correlation is related to fluctuations associated with symmetries, okay? Near degeneracies can appear from frustration, like in a spin liquid, or from so-called dynamical or quasi-symmetries, operators that almost commute with a Hamiltonian but not quite, or just manifolds of low-energy states that are competing with a mean field for being the ground state. So our idea on how to deal with this is to tackle the problem at its root. What we're going to do is try to reduce entanglement in mean field in the ground state using dualities, which I want to tell you about in a little bit. Then, after we're done, we're going to use DFT in this weakly correlated perturbative regime, but just for weak correlation, because all strong correlation will be gone. So what is a duality? It's an equivalence between two theories. It relates a theory in which accurate approximations are difficult to another theory in which they are easier. There are actually nonlinear transformations that preserve the Hamiltonian spectrum, and they can be non-canonical, meaning that the algebra changes, for example, spin to fermions, or canonical, fermions to fermions. Now, the idea here is that mean field theory in the original, which is going to be the physical frame, and the dual representation are different. And in this sense, symmetry breaking is also a change of frame, but it's generated always by a linear canonical transformation, so it's much more limited. These dualities are nonlinear, and they span a much bigger space. And also, they are interesting from the perspective that dualities change the body rank of interactions. So the rank of a Hamiltonian does not stay the same. And they completely transmute short range into long range and vice versa. They completely change the physics, but they are representing the physical physics in a way, in a different manner. So the goal is to find dualities with mean field theory reduces entanglement. That means convert strong into weak correlation. And I'm going to show you two examples. First one is the Jordan-Wigner transformation, which one uses for mapping zero seniority SU2 to fermions, as we do in quantum computing. And the second one, Majorana Jordan-Wigner, which is a fermion-fermion transformation. I don't have time to go through the math. It's complicated. My friends still, I love this. I love your theory, but it's too complicated to understand it. So I'm just going to be conceptual. There will not be no equations. But let me give you a sneak peek. Yes, we succeed in reducing entanglement. I will show you. But there's always conservation of misery, right? So these transformations rely on something called string operators, okay, which are very, very unfriendly to most methods. I'll tell you why. And this is where DFT comes into play, because DFT will not care about these operators at all. It doesn't matter. So what is Jordan-Bingham? Those of you who do quantum computing probably have heard about it. It's a mapping between SU2 generators and fermions. It's used in quantum computation to represent electronic Hamiltonians in terms of qubits. It's a one-to-one mapping of operators and states. If you do exact diagonalization, you obtain identical results with spins or with fermions. But if you do approximations, like mean field theory, you don't get the same result. You get very different results. And the question I asked when I started working on this is, which one is better? Is spins better than fermions or fermions better than spins? The answer was not no. Turns out that mapping SU2 spins to fermions makes things a lot simpler in mean field. It weakens correlations. Now, these string operators appear. They are non-local. They are many-body. They play a key role, and I'll show you that in the next few equations. This is the Jordan-Bingham transformation. You have the spin generators as plus, as minus, as z. They map to c, c diag, or n. And these are the string operators. So when you look at them, you can write them. There's an e to the I pi, which means that when you expand this exponential, you get a product of 1 minus 2 and 1, 1 minus 2 and 2. There are many body. But the quantum chemists in the audience should quickly realize that this guy is a Talvis rotation with fixed parameters. And in the spaces, all the parameters of the Talvis are pi. We know how to deal with Talvis rotations. Anyway, so what the string operators do is they carry the parity of the fermion, and that's what they're responsible for transmuting fermion commutation into spin SU2 commutation. So this is standard Jordan-Bingham. And as I said, strings are many-body, and when you ask people, why don't you do traditional computation, classical computation with these operators, they say, well, they are many-body, you cannot compute with them. Well, yes, you can. So we know how to compute with them. If the density metrics of a Slater determinant is order n cube, then when you put the strings, it's a different rotation for each orbital. It's a different Talvis rotation. For each orbital gets rotated differently if you want. And therefore, this is order n fifth for the whole RDM. So we can do computations with this. So let me give you an example. The one-dimensional XXC model, which is a nearest neighbor interaction. A delta equal 1, this is a Heisenberg model. Delta minus 1, the ground state is very, very complicated, but has a simple structure. All spin configurations have equal amplitudes, but different energies. So this is an equal occupation. Every configuration in the full CI has the same weight. Delta equals 0, it's the ground state. All spin configurations have equal energy, so it's massive degeneracy. The amplitudes are different. It's a maximum degeneracy. And here, HEP is a product state that plays a key role. Not going to talk about that. In 1D, the strings for nearest neighbors cancels out. So this is the transformed Hamiltonian. You can read it here from the slide. And something interesting happens because at delta equals 0, this is a one-body operator. This Hamiltonian is one body. The two-body term is the last term, goes away. So at delta equals 0, when you map to fermions, the Hamiltonian is one body, hard to focus exact. And you say, well, okay, that's interesting. What is the correct answer in terms of spin? It's resonating valence bond, but the ansatz in this particular case becomes this e to the j2 on HEP. It's a very complicated wave function if you think about it, but in terms of fermions, is trivial. It's combinatorial if you do it in terms of spin states, but it's order n cube if you do it in terms of orbitals and hard to fog. What about the entanglement? Well, variational J2 coupled cluster is very strongly correlated, has a lot of terms. Actually, as I told you, all the terms have the same weight. Hartree-Fock, I'm sorry, all the terms have the same energy, but the weights are big. Hartree-Fock is entangled. That's what we call a product state, which in symmetrics, which is idempotent. What about the overlap with the exact ground state? Okay, so here there is, in spin, this is the AGP, which is a much better mean field than just a simple spin configuration. You see that the overlap is lousy. It's practically very, very small here, and it's only 0.2. Whereas in the case of the fermion wave function, you get overlaps, particularly between -1 and 1, which are really, really close to 1. So you have a much, much better starting point to do correlation that you're missing here. The energy is also much better. So here, the dashed lines, this is AGP. This is another type of correlated AGP. But anyway, so Jordan-Wigner is this blue curve. And if you correlate with couple cluster, which I can here because I don't have strings, I get very, very good results. All right, so that's for going from spins to fermions. Our Hamiltonian, the electronic structure Hamiltonian, has two color fermions, C diver up and C down. We're going to map that to different fermions, A and B. And to do that, we're going to do two steps. In the first step, which I'm not going to explain the details, we use something called a Clifford algebra rotation, which you introduce Majorana operators to do that. And essentially what you end up doing is map from two fermions to an SU2 times another fermion. This SU2 actually is going to carry the seniority 0 part of the algebra. So in the second step, what we do is we map the SU2 to a second set of fermions with Jordan-Wigner. And as I said, the A diver fermions now are going to represent the SU2 algebra, which is the seniority 0 algebra, which in this case is a mixture of spin and pairing. Spin and pairing get mixed up into a single SU2 algebra, which is represented by A. And the B fermions are the ones that break seniority, and they will create the rest of all the other configurations in the space. And here are some results, proof of principle, to show you that that Haber model away from half-filling that I told you, unrestricted CCS ETQ cannot get right, the overlap of GHF in the original physical frame. This is the physical frame of up and down fermions. The overlap of GHF is awful. That's why if you do coupled cluster on this, you're not going to get really good answers. I mean, I said UCC SDTQ, but GCC SDTQ is exactly the same. Whereas in this other dual frame, okay, then the mean field, which is written here, it's much, much, much better. What about the energy? Okay, so double whammy. The previous slide shows that I was able to reduce entanglement. This slide proves that my energies with this MJW are much, much lower than the ones I obtained with generalized Hartree-Fock. Right, so just to conclude, because I want to leave a lot of time for questions, the idea here is to use dualities to reduce entanglement and improve the overlap with full CI. And I show you just one possible transformation of many that are in potential one can do. So the idea, in other words, is to convert strong into weak correlation. The weak correlation regime has a universal answer. That is couple cluster theory, CCSE branches T, or you put quadruples, whatever. Doesn't matter if you are weakly correlated. Doesn't matter how you are weakly correlated. Couple cluster gets the right answer. If you're strongly correlated, you have to find a different technique for each and every Hamiltonian. Strong correlation is Hamiltonian dependent. There is no universal prescription for it. But if you can use one of these dualities to transform the system into something else which is weakly correlated, then you're back to a problem that you know how to solve. But as I said, conservation of misery dictates that this could not be for free. What comes and bites you back are the string operators. They are tailless rotations, so we know how to handle them if we can put them right next to the slated determinant. Then it gives a rotation of the slated determinant, and we know how to do this non-orthogonal matrix elements. But think about couple cluster. So I have my mean field, my Hamiltonian has been transformed, has these A and B fermions and these tailless rotations. And now this is my mean field. I want to do couple cluster. What do I need to do? Put e to the t2 plus t3. Okay, but here's the string operator. He needs to be right next to the determinant. So let's commute it. Okay, now it gives me a many-body operator to all orders. That's the problem. So I need to have correlators that commute with the string operators. We're working on that. There are some things that can be done. But DFT doesn't care about doing DFT in an orthogonal representation. So at the end of the day, if this is successful, we will be doing sort of non-orthogonal type matrix elements in the presence of a Hamiltonian that has some higher rank body terms. It goes up to 4, not too bad, and just working with non-orthogonal representations. Thanks to the OE-NSF World Foundation, Gaussian, who hasn't canceled me yet, and thanks very much for your attention.
Thank you very much, Gustavo. Comments and questions from the audience? John?
So Gus, it's an interesting talk. I want to go back to something that you said near the beginning of your talk. I think you said that in an antiferromagnetic solid, there's no spin symmetry. Is that right?
Yeah.
How do you know that?
Because that comes out of neutron experiments in a way. So what they do is a spin-spin correlator that is antiferromagnetic, but there is no. I mean, if you put a magnetic field, you don't get a response in lowest order. So when we model that with DFT, you have spin density at the nuclei, and that is not correct. The spin-spin correlator of the unrestricted Conchamp calculation it's okay, and the gap may be okay, but for the wrong reason, not for the right reason.
Yeah, Martin?
That's an experiment.
It compares relatively well to experiment. The gap, the band, at least with HSC, the band gap, it's very, very good. The spin-spin correlator the density of states is also very good. The spin-spin correlator is not as good, and of course, you know, it's antiferromagnetic, so there should be no spin density at the nucleus. I mean, if you freeze it, then you will see it, but it's entangled.
Very interesting talk, Gus. Especially I was intrigued by your early comments about symmetry breaking, and wanted to ask you, do you have any example that you could share with us about a case where there is a strong correlation and Hartree-Fock does not break a symmetry, in a molecular example from any row of the periodic table?
No, Hartree-Fock will break symmetry because there's always a pairing talking to spin, and spin symmetry will break like an hover away from half filling. But that symmetry breaking is now not enough to describe the strong correlations that are occurring. They will describe them only when they are in the spin channel, when this is sort of in the ring channel of the many body. But if it is on the pair, so I should have said that. What is a pairing degeneracy? It's the simplest way to understand it is you have orbitals that count down in the mean field, but now it's a double excitation into the HOMO to the LUMO, and maybe LUMO plus 1, LUMO plus 2, and everywhere. So it's not just one pair, it's multiple pairs that become. So what states in mean field can mimic that? Oh, let's go to n plus 2, n plus 4, n plus 6, n plus 8 electron determinants and put all the pairs in all of the states. And then, well, that's the BCS Hartree-Fock Bogoliubov state. I say, well, let's do that. The problem is, okay, which orbitals do I use? What state do I use? If you don't break number symmetry spontaneously, all of those states are going to have higher energies. They're not going to be useful. So the energy lowering is what matters in mean field symmetry breaking.
So the correct takeaway then is that symmetry breaking is a good diagnostic of strong correlation, but not a cure.
A cure in the spin case, it is fine. I mean, we know that if there are no pairing correlations and restricted CCSD, it's pretty good. I mean, you can see how you put triples and quadruples and symmetry comes back. I mean, as you build towards full CI, symmetry comes back. the spin symmetry comes in.
Kieran?
Right at the end, Gus, you were saying, well, you can do, when you've done the transformation and things are weakly correlated, you can do couple cluster and then also maybe DFT. But DFT depends on the one body piece being a function of R in real space, being diagonal in the real space representation to get the Holmberg-Kohn theorem. That won't be true anymore.
Yeah, so you do the mapping and you get the mean field and you grab and now you think about what is this mean field that I have obtained in the original frame. It's a very complicated wave function. And then you say, well, what is this thing missing? It's only missing dynamical correlation. Okay, let's do blip.
So you're going to go back to the original.
Well, you just grab the blip functional, you map it, and then you work it in the dual representation, not a problem.
Oh, okay, okay.
Or you call your friends who have talked about, discussed in the past, Andreas, you, John, about translating, functionals into different frames. You guys have advocated, that we use the on-top pair density and other. So it's a whole thing soon to be explored. But the simplest low-hanging fruit is just grab the functions that we know are for correlation, translate them, and use them. See what we get.
Okay.
Per, you
Yeah.
want to say something?
What I say is, can be a complete misunderstanding, but I take the risk. And then H2, you break the curve, you get at some point spin or symmetry breaking, right? If you allow it. So when you do a closed shell and you break it, it will go up and down somewhere in this continuously. So that's not how you do it. You do it with alpha spin here, beta spin there, and you combine it. That smoothly goes into H2, which is entangled, and not a problem. That it's purely technical problem, but this is.
If you start from two spins or infinitely apart, you are not in a singlet. You are in a superposition of
That's
a singlet
right,
and
of
a
course.
triplet.
Yes, but I don't have to force symmetry anywhere. It
But
just
you're
goes
you're-
automatically over to.
Yeah, but you're violating quantum mechanics. If you are in a singlet, you cannot. You
don't
are
care.
in this. You're in this. In the
Yes,
in the
spin is
UHF basis of pair,
Yeah.
you are in an open shell singlet. In the RHF basis, you are doubly exciting from sigma g squared to sigma u squared.
Offer the spin, which is not so energetically important. That is what you have to do with DFT. When you have just a single determinant, you have to say that you don't care about the spin, but the energy is fine. It's perfect.
He's taking some water. And Paula?
Yes, you only talked about breaking spin and number symmetry. What about spatial symmetry?
Yeah.
Because
It's also a linear canonical transformation at the end of the day. So if you have a Z2 symmetry, whatever.
But sometimes you can have strange spatial
Yeah, but what
symmetry.
happens is that because point group or translational symmetry is discrete, it piggybacks on the continuous symmetries, typically spin. But the same story. You can also break translational symmetry and not spin symmetry, or break spin and not translation. But most of the time, in realistic systems, they break together.
Yeah, okay. But you could also have strange things, right, to mimic strong correlation.
Yes, but I think that
Localized
all of
orbitals in
those,
strange
I mean,
ways.
if you have a charge density wave, you don't have to break number symmetry for that. Okay, so you can, that's only breaking translational symmetry without, you can have a charge density wave with spinless fermions. So there's no spin whatsoever.
Yeah.
You have a honeycomb lattice and you change the charge. And then that's a charge density. You don't have to break number symmetry for that.
No, I agree. But in a more complicated systems, you could have strange spatial symmetry breaking in which your mean field orbitals are localized in strange places, and actually you can have several.
Yeah, that's part of what I said. So I
Okay.
started saying the most common spin symmetry, most common symmetry breaking and relative and important for chemistry is spin symmetry breaking. But then, there are other, not all strong correlation is related to symmetries at all. So you're still talking about symmetry. I'm saying there are low-lying manifolds of states.
Yeah, exactly. No, that's what I'm talking
Well,
about.
those are called, we can call them dynamical symmetries or quasi-symmetries. And there are ways
So
you can.
essentially, you localize your in-field orbital somewhere because it's where the electrons in reality are entangled, but they are most likely in some regions, and then you better localize them. But this can be very strange.
But it's Hamiltonian dependent. That's the important thing.
Yes,
and there are techniques you can use at the generated coordinate method to try to integrate through the coherent state to try to capture that. And good luck finding the coordinate because you don't know. It's Hamiltonian dependent. A priori, you don't know what it is.
Okay, maybe we should then say thank you very much for your presentation.